G'day. In this video we are going to plot the psychometric functions. Well, actually we're going to see how the psychometric function, we're going to use a Gaussian cumulative distribution function as our model, how the CDF, cumulative distribution function, relates to the probability density function of the same Gaussian curve. So we use the CDF quite a lot when we analyze our psychometric data. So I've given myself a challenge. I've got 10 minutes to do this with you to try and show how the PDF, probability density function, relates to the cumulative distribution function, which is our psychometric curve. Okay, so we know that when we do our experiments, we're going to have a y-axis for our figure, and that's going to relate to the stimulus intensity that we present to our animal or our human, and that we know on the y-axis we're going to have a probability correct, and that's going to go between 0 and 1. What we're going to do is we're going to use a Gaussian curve to model this psychometric function. Let's get cracking. We're going to import right at the start OS, and we're going to import from datetime, import datetime. This is just my standard opening, and what we're going to do is we're going to clear the output if os.name equals nt. So if you're running a Windows machine, it's going to pass CLS, or else it's going to pass clear. Oh, we need that there. And then we're going to print out date time.now. We're going to string format that because all I want is hours, minutes, and seconds. If we've done this correctly, hopefully we should. Okay, so we've cleared the output and we've got a nice clean blank slate. Now, let's start working on our x-axis. That's going to be our stimulus intensity. Now, I'm just going to throw some numbers out there. Let's make our stimulus intensity an array of numbers from 0 to 100. So if we're building arrays, we need to import numpy as MP. That's just a standard way of getting numpy in there. And MP A range, it's going to have a start value, which is 0. It includes the start value and a stop value. We'll make it 105. And we're going to go increments of 5. Actually, we'll make it increments of 2. Okay. So it's going to start at 0, end at 100, because remember the A range function does not include the stop value, and I encourage you to play around to figure out just how you go about generating the correct stimulus intensity, or the stimulus array. So if we print now stim intensity, okay, we should see an array of values going between 0 and 100 with an increment of 2, and that's what we've got there. Brilliant. We're at 2 minutes and 36 seconds. We're running a little bit behind time. Now we want our probabilities that are associated with each of those stimulus intensities. So we want from scipy scipy.stats, we want to import norm. We just want the normal distribution. We don't want a Gumbel or anything like that. So PR equals norm.pdf. We want the probability density function, and we want to calculate it over the range of stimulus intensities. So stimulus intensity, and now we have to give it the mu, okay, or the average and the standard deviation of the model. Okay, so we'll say mu and SD. Okay, and so if we have, let's just say the mu is, say, 50, which is about halfway across our stimulus intensities, and the standard deviation of our Gaussian curve is going to be 20. Okay, so now this here should return the probabilities for this function at mu and standard deviation across all of these stimulus intensities. Now we want to plot it. So we want to import matplotlib.pyplot as plt. I'm not going to create any figures and axes objects. We're just going to use the standard subplots. Okay, so plt.subplot. Now, row of 2, 1, 1. So two rows, 1 column, first position. Plot.plot. Now this needs an x stim intensity, and we need to give it the y values, which is going to be the probabilities here. I want the color to be black. Whoops. I want the marker to be, say, just circles. I want the line width to be 2. I want the line style to be dashes. Okay. Now, I want to limit the x-axis to go between 0 and 100, and I want to limit the y-axis, or maximize our y-axis. Okay, so it shows all of the values between 0 and mp.max, and I want to give it PR. So I want to take the maximum value from this array here and use that as the limit. So therefore, as the maximum value changes, we're going to maximize our values that we can see, or on the y-axis, so it's not going to look too bad. And then we're going to show this. Let's see what we get. Hopefully we should see a figure or a plot with a Gaussian probability density function, and there we can see that there. Nice. Okay, PDF with a mu of 50, okay, and we've got a standard deviation of 20 there. Okay, we'll quit out of that. I don't want it to be at 2, I want it to be at 5. That looked a little bit too confused. What I want to do now is I want to plot the CDF. So this is the cumulative distribution function. So if we go norm.cdf now, this takes exactly the same arguments as the PDF. So we want to calculate the cumulative distribution function for all the intensities with a model with the same mu and the same standard deviation. Now I want to plot this underneath the first one. So plot.subplot 2, 1. This is in the second position now. The second position is under the first position, and so we want to plot stim intensity. We want CDF, PR, the color. We'll make the color, we'll make it blue. We'll make the marker also circles, line width equals 2, and the line style equals ... So we'll have it dashed. Okay, we want the x-lim to be the same as the first one. Now for the y-lim, okay, plot.ylim, we know that the CDF will only ever go between 0 and 1. So if we plot this now, we should now see two figures on this plot. Upper plot will be the probability density function, and underneath we will see the cumulative distribution function. Okay, so if we add up now every single value, successive value on our probability density function, okay, and we add up each value onto the sum of the previous values, we get the cumulative distribution function. So we can see that as we get to halfway on our PDF, the cumulative probability is 50%. So therefore, a mu of 50 will give us a mu of 50 in our CDF. Standard deviation is going to give us the slope of the CDF. We're at 7 minutes and 10 seconds. So now what I want to do is I want to show you how changing the standard deviation, okay, changes the slope of the cumulative distribution function. So here we've got we'll make it 10. Okay, so we're going to have a narrower probability density function now. So PRSD1 equals norm.PDF. We still want it over the same intensity, mu, but now we want it over the first standard deviation. And we're going to do the same thing for our PR, our cumulative probability. So norm.cdf, stim intensity, mu, and now we want SD1. That'll be underscore 1. So now let's add to our first plot here. Let's add on, okay, let's add on another plot. Okay, and what we want to do is we don't want PR, we want PRSD1. Okay, we'll have it, instead of black, we'll have it as, say, red. Okay, and what we're going to do here is we don't want the maximum Y value to now be taken from the first PDF. We want it taken from the second PDF, and I'll leave it to you to figure out why we would want it for the second PDF when we have a narrower standard, or we have a smaller standard deviation. Okay, CDF PR1. So now this is not going to be blue, this is now going to be red. We'll make this one black, so now we can compare across the two. So hopefully if we've done this correct, we should see now a second curve appear on the upper and on the lower figures. Now I've got a spelling mistake here. I've got my, not mu. Okay, so that's my bad there. Oh, we're at 8 minutes, 9 minutes now. Here we go. Brilliant. What do we have? We have two probability density functions. The first density function here in black, we've got it quite broad because remember the standard deviation was 20. As we narrowed the standard deviation, or we've reduced the standard deviation, what we saw is that the curve now becomes quite narrower and a bit taller. It still has the same mu, it's just the width is smaller, the standard deviation is smaller. What do we see here? The red function here is for, again, the probability density function, or the cumulative density function actually, with the smaller standard deviation. The red corresponds to the red here. And what we see is as we narrow the standard deviation of the probability density function, we actually increase the slope of our cumulative distribution function. The average values, where it sits at 0.5, stays the same. All right, I'll leave this video here. All the best. 10 minutes.